Hello friends, welcome again to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss spectroscopic problem from the CSIR NET examination of 2018. So we will cover both the sessions, like questions which have been asked in the June examination as well as in the December examination. Today we will discuss all these problems, and total 11 problems we will discuss step by step with every detailed explanation. Okay. So without wasting time, straightforward we can go to the question, and if you read the first question, what it says: mass spectrum. You see here, mass spectrum of a compound shows M+2 peak, right? So M+1, M+2, these peaks are the isotopic peaks, okay? Shows an M+2 peak, ion peak, that is about 4% of the molecular ion. That means whatever the intensity or abundance of your molecular ion would have, the 4% of that intensity will have this M+2 molecular ion, M+2 ion peak intensity. Okay, so this indicates that the compound has. So that means if this happens actually when your compound is showing the M+2 peak, which is of about 4% of the molecular ion peak, then you have to predict which one can be possible in your compound. Like fluorine, first option; second is the sulfur, and third is the bromine, and fourth is the chlorine. So this question is actually nothing to do with the exactly a mass spectrometry. So if you have only knowledge about your percentage abundance of the different isotopes, then you will be able to solve this problem. So please remember, first I am going to explain this fluorine. Okay, so this fluorine, I can tell you, this is 100% pure, isotopically pure. Okay, isotopically pure I can write. What is the meaning of isotopically pure? That means no other stable isotopes of the fluorine would be there. Okay, so that means there is no possibility of any kind of M+ of M+2 peak, right? Since you know this is isotopically pure, so you can immediately discard this option A. This cannot be your answer, right? And then you have to look for the another options, like say you are having halogens, like you are having chlorine here, and you are also having the bromine here, you are also having the sulfur. Okay, so if you check the percentages of this, so you will have the chlorine 35, this is the first isotope, and that chlorine 35 is roughly 77.5%. its percentage abundance is 77.5%. and then you have chlorine 37, right? Chlorine 37, and that chlorine 37 is having the percentage of 22.5, right? This much of second isotope is there, and remaining would be the other isotopes to make the 100% of it. So if you see these things, so if you multiply 22 with 3 actually, right? So it will give you roughly value which is close to the 77. So what indicates that if the intensity of if you check the intensity on the basis of the percentage abundance of these two isotopes, okay, so what will happen? The ratio would be like that, 3:1. Okay, so because if you multiply this 22.5, so it will come close to this one. But in the question itself, it is given that the intensity should be 4%. Okay, but here it is not possible, right? So what happens in that case? If the molecular ion peak, see, because isotopic peaks are generally those peaks which are due to the less abundant isotope. Okay, so 77.5% is your most abundant isotope. That means molecular ion would have the intensity of the 3, right? And isotopic peak which would be M+2, because it is 35 and it is 37. If you add 2 on this 35, it will make the 37, but the intensity of that 37 would be roughly 1. Okay, M+2 peak would be 1. So this chlorine can also be opted out from here. So this chlorine cannot be your answer. Okay. Similarly, if you go for the bromine, right? So I am writing here for the bromine. So bromine 79 is there, that is Br. Okay, and roughly its percentage is 50.68%, right? And then you are having the bromine 81, and its percentage is roughly 49.3. Clear? So they are roughly 1:1%. What happens that what is the meaning of that? If your molecular ion peak has the intensity of 1, then molecular, then M plus 2 peak would also have the intensity of 1. But in the question itself, what it is given here, you can see here it is given that M plus 2 peak should have the intensity of the 4%, but this indicates that the intensity of the 1%. So on the basis of this, you can discard this bromine option here. Okay, so what you left with the sulfur. So your correct answer is the sulfur. Okay, sulfur would give you this value. So how the sulfur will give you this value? This is again quite very simple. You have the first isotope of the sulfur, which is S32, which is roughly 95.02%. Please remember this value. Okay, and then you are having the sulfur 34. Okay, and sulfur 34 is having the percentage of 4.21%. So it is quite clear that if you consider this as 100%, if its intensity, molecular and peak intensity is 1, then it should be of your 0.4. Okay, 0.4 means that means roughly 4%. So this sulfur is the correct answer. So you should know you should actually remember the sum of the isotopic percentages. That's only then you will be able to solve this particular problem. So this was however the very easy problem. Now moving to the next problem, what it says that number of signal observed in the 13 CNMR spectrum of the following compound. So it's a compound, it's a natural compound. Okay, we study such type of compound in the natural product chemistry. So there is no need to know the name of this particular compound. So how many different kinds of the carbons are there, that would decide the different kinds of different numbers of the carbon signals in the spectrum. So if you put the mirror plane from here, okay, if you put the mirror plane just like that, okay, so this will render this half and this half identical. Please remember. So how you can do that? Say if you put this mirror plane here, right? This mirror plane if you put here, so what will happen? This half, this carbonyl carbon and this carbon, this carbonyl carbon and this carbon, they are the same or identical type. That means they are the mirror images, kind of mirror images. Okay, so they are identical, so they will give you the same kind of the signal. Okay, so what you can do, you can simply mark them. If you mark this carbonyl carbon as 1, then automatically this would also be 1. This would also be 1 because they are of the same kind. Okay, if you mark this as 2, then this would also be 2, right? But in the rest of the part you will not find the mirror plane due to the presence of these two groups. Okay, and if you have seen my previous lecture on this bicyclo compound, stereochemistry of the bicyclo compound, then you will be able to understand how to visualize such kind of the molecules. See, in stereochemistry, visualization or thinking is very, very important. You have to memorize the things, and you have to think that how the plane will go in this molecule, what will happen, right? All these things you have to memorize, right? Now for the simplicity, what I can do, I can remove this mirror plane, right, because I have explained the things on the basis of this. Now what you left with the different kinds of the carbon. So what you can do, you can mark this carbon as carbon number 3, then you left with the carbon number 4, and then you left with the carbon number 5, and this carbon is the carbon number 6, right? So you cannot say that this carbon, which is 3 and B, they are not identical. Why they are not identical? Because here C double bond O group is there. So total 6 kind of the different carbons are there. That means 6 NMR signal you will get. So correct answer in that case is the 6. Now moving to the next problem, what it says that, so due to the problem of the space, so I have shifted this question on the right hand side. Okay, and then you can read the question very carefully to solve the question. Okay, however, I have solved such type of question many times in the previous year examination, because whenever the question from the substituted benzene is there, then you have to look for the your para, ortho and meta isomers. So this idea actually basically comes from the proton NMR spectrum. See, this is the proton NMR spectrum. The compound shows the following spectral data. Proton NMR spectrum, which have this doublet at 7.9, and you are having another doublet at 6.6. And I told you many times in my previous lectures, in the substituted benzene, if you have this kind of the pattern, two doublets are forming, then straightforward you can conclude your compound is para-di substituted. Your compound is para-di substituted. So if the students who are following my lectures regularly, they know that these things I have told you many times. So whenever your compound, see, if your NMR is suggesting the para-di substitution, then you can very immediately discard this option C from here, because it is your ortho substitution. If this is the functional group, this carbon is the ortho carbon, so this is ortho, so you can discard this. And if this is the functional group, this is ortho, this is meta, so this is meta substitution. So straightforward you can discard the option C and the option D. See guys, this thing is very very important in CSIR net examinations especially, right? And also in the gate examination. If you have properly studied a particular topic, then out of the 4 options given, you can immediately discard 2 options from them based on your knowledge. Okay, then there would be a competition between the 2, which would be actually close to the your correct answer, but in these 2 you have to select the more correct answer. Okay, now I am going to explain. You have discarded this one. Now I am going to explain the proton NMR spectrum of these 2. So guys, if you check the chemical shift, right, so what can happen here, you can see it is given at 7.9. You are getting the doublet at 7.9. So what you can do, that 7.9 value for this particular carbon, this is 7.9 ppm, this is 7.9 ppm. Okay, and then you are having the 6.6, a doublet at 6.6. So this carbon is at 6.6 and this carbon is also at 6.6. So how you can differentiate why actually these are having these downfield chemical shift? Due to this carbonyl group. This carbonyl group is electron withdrawing. It will suck the electron density towards itself. So what can happen? Here electron density is less. So these carbons are de-shielded, and de-shielded carbons have the downfield shift. Downfield shift means the downfield shift means your higher value of the ppm. So it is at 7.9, it is at 7.9, it is 6.6, it is 6.6. okay, then you come this 4.3, and it is a 4.3 quadrate. Okay, 2 proton quadrate at 4.3. so immediately you can jump out on this one, right? So this will give you the value at 4.3. why? Because 2 protons are here, 1 proton here and another proton here, and this is the methyl group, 3 protons are here. Okay, so if you apply the 2ni plus 1 rule, here 3 carbons are there. Okay, and it will split into a quadrate. 3 plus 1 4, that will give you the quadrate. So see what is the formula for multiplicity. Multiplicity equals to 2ni plus 1. So here 2 is the constant, n is the number of the neighboring hydrogen atoms. So if you are looking for the signal for these 2 hydrogens, then you have to check in the neighboring carbon atom how many hydrogens are there. So 3 hydrogens are there. So what you can do, you can straightforward put 3, and this quantum number for proton is half, that is the plus 1, right? And these 2 will cancel out. It will give you the 4, that means the quadrate. So this value at 4.3 guys, it is a quadrate that belongs to the 2 proton. Please remember, there is no need to remember the coupling constant in that case, right? Similarly, if you focus on this one, so this will give you the 3 proton triplet. So you can write for these this methyl group, right? On these 3 proton triplet you will get, and that 3 proton triplet you can see here where it is. It is at C 1.4. So you can write the chemical shift 1.4 ppm. Okay, and then what you left with the this signal at 4 broad. See, due to the exchange with the deuterium oxide, right, which is the solvent, in that case, the signal actually gets broadened. However, this exchange is not very fast in case of the amine compounds. That's why this is not that broad. But if you take the acid or some other compounds, in that case that signal would be very very broad, but in that case not that broad, but it will be broad. Okay, so the signal which you are getting at the 4 ppm for this hydrogen, okay, this is basically due to the 4.0 I am writing here ppm. This is due to the protons attached to the nitrogen, because nitrogen is actually electron withdrawing, so it will cause the downfield shift. So this is the proton NMR spectrum of this one. But if you check, guys, if you check the proton NMR spectrum of this species, almost this kind of NMR data which is for the option A would be there for the option B also. Please remember, it is very, very important. So here you will have the little difficulty in understanding the chemical shift. How? You see, what I told you, this is what electron withdrawing group. So these two carbon would have the downfield shift. When they have the downfield shift, so you can write for these 7.9 and 7.9. Okay, and then because this chlorine are there, they can push the electron density here in the ring. So these are the shielded nuclei. So you can write 6.6 and 6.6 for them. And for NH, for these hydrogens, I already told you this is 4.0 broad signal. Okay, and this what 2 proton quartet, and this 2 proton quartet would be somewhere around at 4.3. Please remember. And here this is 3 proton triplet, and that 3 proton triplet would be there somewhere around 1.4. So it is very difficult to understand. So how actually we can conclude that which one is the correct? So here I am giving you a very, very important trick. Very important trick I am giving you. See, generally what happens when you have this NH2 group, right? I am writing NH2 group, right? And see, if this generally what happens, if this NH2 is aromatic in nature, if this is aromatic in nature, so its chemical shift roughly goes in this range 3 to 5 ppm. Okay, and in the question you are saying that this NH2 is giving the peak roughly where it is this 4.0. okay, the peak is there in at 4.0. see, let me check what is happening here. Okay, so what we can see, we can see here in this option 2, what I told you, roughly aromatic protons, they will give you this value here between 3 to 5, and it is given that at 4 ppm you will get the answer. But you can see here this carbonyl group is in option B. This carbonyl group is there attached with this nitrogen, and it is the electron withdrawing group. When it is the electron withdrawing group, it will suck the electron density towards itself, making these protons de-shielded. And due to the presence of this carbonyl, if this is de-shielded, their original value, actually if you check the spectrum, will not come at the 6 ppm, but it will not 4 ppm, but it will come somewhere around at 6 ppm due to the presence of the carbonyl group, right? But in the question itself it is given that the value is 4 ppm. So on the basis of the chemical shift of this NH2 and which is flanked with this C double bond O, you can discard the option B also. So what you left with the option A, and that option A is the correct answer for you. So this is how, see how the these affect the general organic chemistry is very, very important. And I told you many times, guys, if you don't have the solid background in the general organic chemistry, then you will be you will face quite a difficulty in solving the spectroscopic problem. Okay, now moving to the next problem, what it says that, right, this problem is again a very simple problem, but again this problem is simple for only those people who actually understand the molecular orbital diagram. But before actually going into the details of this question, I want to go back actually, right? So what I missed here, guys, in that case, you see, I missed here this mass spectral data, right? However, see, according to me, see, generally people actually when they explain this problem, they also explain the mass spectrum. But according to me, there is no need to go for the mass spectrum of this compound. But if you want to go for the mass spectrum of this compound, then you will be easily able to differentiate between these two. Okay. Because this compound A, actually it will give you, it will undergo the McLafferty rearrangement. Okay. So what I can do, I can see, it is better for the beginners actually to understand each and everything which actually I missed. But for me actually, for the time saving purposes, that's proton NMR is enough for me, right? But for you guys, I am going to explain this also. Say for example, this your option A is the correct answer, which is say this one. I am writing NH2 here, okay, and this is O, and this is just like that. And in that case, you see guys, the Mac-Lafferty rearrangement will take place. So how the Mac-Lafferty rearrangement will take place in that case? So you see, this is the carbonyl group, this is alpha part, which is the oxygen, this is beta, and this is gamma, right? And that gamma is having 3 hydrogens, you know, 1, 2 and 3. And what is the Mac-Lafferty rearrangement? Transfer of the gamma hydrogen transfer of the gamma hydrogen to the unsaturated part. Okay, so if you make this molecule, if you make this as molecular ion by bombarding this with the high energy electron, then you will get this molecular ion, and after that you can very easily apply the Mac-Lafferty rearrangement. See, in my previous questions also I have explained you the Mac-Lafferty. Okay, so here Mac-Lafferty rearrangement would occur, and in the Mac-Lafferty rearrangement what will happen? One of the gamma hydrogen along with the one electron will go to this, okay, and one electron will come here. And since you know the alpha cleavage is the very relevant cleavage in the Mac-Lafferty rearrangement, so what will happen here? This bond will break. When this bond will break, this electron will go there, and one electron will come here. Okay. Similarly, one electron will go up and another electron will come here. So what you will make after this fragmentation pattern? This is your oxygen, NH2 will remain as such. This was your, you see here, this is your carbon double bond oxygen, but one electron has shifted up and one electron has shifted here, and hydrogen has shifted from here to here. So this is a single bond OH now. So what you can do, you can write OH here, okay, and this would become now double. Why it has become double? Because when this bond has cleaved, one electron actually transferred from here and another electron transferred from here, and you see here you will have the neutral fragment, which is CH2 double bond CH2. Okay, so this ion you will form actually, and if you check the molecular weight of this species, whole of this species, this is M by Z 137, which is a very important peak, and M by Z 137 is there. And this M by Z 137 is not possible in that case because there is no gamma carbon in that case, right? No gamma hydrogens are there, since gamma carbon is not there. So Mac-Lafferty rearrangement is not possible in that case. See, this is the one way. However, you can also explain this molecule, this peak at 120 actually, right? So this 120 you can very easily explain, and after that this 92 you can also very easily explain. But I think there is no need to go in that much of the detail. But if you want to know, or if you want to learn the mass spectrometry or fragmentation pattern completely, then you can type in the YouTube search bar mass spectrometry by tetrahedron chemistry classes. Then you will find the playlist there, and in that playlist I have explained all these things. Okay, now moving to the next problem. This problem has taken quite much of time. Now what my next problem says, consider the nature of the solvents. So you have been given the solvents and the nature of the solvents like that. First solvent is non-donor, second is the weakly donor, third is the strongly donor, and next is the pi donor. Okay, and the corresponding lambda max, and these are the lambda max which are given here, right? They are not actually related to these. You have to match them, right, in the various solvent given in the list 2. And for the iodine, you are looking for the transition, right, electronic transition for the iodine. And in the vapor state, you know, if you have done the thin layer chromatography, or say if you have the natural product chemistry, if you have done the natural product chemistry experiment, you know this iodine is the crystalline solid, and if you actually open the bottle or the container of that iodine, its vapor will go from there, sublimation would occur. Okay, so in vapor stage for this iodine, the lambda max value is 520, but if you dissolve this iodine into these solvents, so what will be the change in the lambda max value? You have to match this change actually, right? So to solve this particular problem, first of all you need to understand what kind of the transitions would occur in that iodine, right? So this iodine, guys, you can see what this iodine is. This is I, this is single bond I, and of course the lone pairs would be there. 3 lone pairs would be there. Okay, and you know this is the sigma bond. What you can do, you can straightforward go for the molecular orbital diagram of this one. So this is the molecular orbital diagram of the fluorine. Okay, and it doesn't matter whether you have the fluorine, okay, or you have the chlorine, or you have the bromine, and you have the iodine. Okay, it will not make any difference. Intentionally I have actually taken this fluorine diagram here, otherwise I can take actually, right, I would have taken that iodine straightforward, but it will not make any difference, right, unless and until the value of the energy levels are given. Okay, so in that case you can see here this is the fluorine diagram. The only change would, if you write I2 here, the only change would be in the principal quantum number, these two values, nothing else, right? Otherwise the transition would remain same. So if you check this one, what you can observe here, these are the HOMOs, highest occupied molecular orbital, and this is the LUMO, lowest unoccupied molecular orbital. So whatever the transition actually would occur, that will occur from here to here. Okay, but we are not looking for these transitions. So I am dissolving. So main transition is what? Pi antibonding to sigma antibonding. Please remember, I am writing here the important transition is what? Pi antibonding to sigma antibonding, right? And pi antibonding is the G rate and sigma antibonding is the G rate, right? So this is centrosymmetry, the property of the center of symmetry. So what will happen in that case? You see here, if you have such kind of the solvent which is a non-donor. So in case of the non-donor, what will happen? Nothing, no interaction. This solvent will have no interaction either of these two orbitals, because if it is a non-donor, it cannot donate electron in these orbitals. So there is no change in the lambda max value if you have the non-donor. So for these non-donors, the value would be same as 520. It simply says that this option A is matching with the option 1, right? So here you can immediately discard those options in which A is not matching with the 1. So here you see in the first option A is matching with the 1. In the first option A is matching with the 1. This could be your answer. But in the second option A is matching with the 3, which is not possible according to us. So we can remove this option from here. Okay. On the same basis, here you see A is belonging to the 4. We can not choose this as the correct answer. So we can also remove this value from here. These two options. I always I already told you, and I always actually generally say this point in the CSIR NET as well as in the GATE examination. You have always this facility to avoid or to discard the two options. Now you left with the next other two options. Either 1 or 3, anyone could be correct. Now you see here, I am going to solve further. Second case, say it is my very strong donor. Very strong donor. What will happen when strong donor is there? Please remember, when strong donor is there, so it will very easily donate electrons to this antibonding orbital, right? And when this donates to the antibonding orbital, so antibonding interactions increases. Antibonding nature increases. Antibonding nature increases. So what will happen when the antibonding nature increases? This energy gap increases. This energy gap increases, right? So for I am writing here, for strong donors, this energy gap, which is in between this pi and sigma antibonding, this is increases, right? And you know E equals to Hc by lambda. When energy increases, then lambda goes down, because they have the inverse relation. So in case of the strong donor, right, lambda max should be low, right? So we can check which lambda max is actually low. In that case, strong donor 520, we have already seen that. Next possible value, which is for this strong donors, which is what, your 360. So that means B should belong to this 360. So you can immediately match them like that. In case of the strong donor, this will match with this one. That means A is matching with the 1, then your C must match with the 4. Then check whether C is in which option C is matching with the 4. So here this C is matching with the 3, but in the option third C is matching with the 4. So A cannot be your answer, guys. Please remember. So you can very easily discard this A also, and you left with the option C. So in that case your option C is looking the correct answer. So there is no need to go further. But see, you can go for the further explanation. These are the weak donors. They will also donate electron here, but weakly donor. So when they are the weak donor, so that much of energy difference will not increase here. So however, the lambda max value will decrease, but it will not decrease. That much decrease will not occur, which happened for this strong donors. Okay. So next value C, weak donor, actually would belong to the 450. Right? You should know this point. Okay. So here you can weak donor this one, and finally pi with 2. So if you apply all these things, then option 3 is looking the correct answer in that case. So you should know the donor ability, right? So donor ability means, you see, your strong donor followed by weak donor and followed by pi donor. This you should know. Okay, this is very important question. Lots of concepts are involved here, and you should know each and everything about the questions. Now moving to the next question, what it says. Right. This question again, it's not a very simple question. It again involves lots of concept or lots of knowledge for to solve this particular question. So how actually we solve this question? It is very important. Okay, say you have been given this cyclooctatetraene. It is a tub-shaped structure. It's a non-aromatic compound. Please remember, I can write here. It is non-aromatic. This is non-aromatic. Okay. However, some people can argue that it is following the 4n+2 rule, so it should be actually this one, but it is non-aromatic because it is not a planar structure. Please remember. Okay. And then this compound, which is formed by the protonation of this. How this compound is formed? I can write the equation like that. Say if you have, right? Sorry. See, this is cyclooctatetraene. Just like that. Put 2 double bonds here, 2 double bonds here. If you have acid H positive, so what can happen in that case? Say this electrons will come here and they will attack on this, and it will result in this species. This, and this will have 2 hydrogens now. See, 1 hydrogens were already hidden here in all the cases, right? And then you will have a positive charge over there, right? And this structure, guys, can be very easily drawn in that manner. Please remember. So basically it is the special class of the aromatic compound, and which is homoaromatic. See, I have covered the aromaticity lecture in pretty much detail, but way back I have covered this topic, but I forgot that whether I have made a lecture on the homoaromaticity or not. If I'll check the playlist, and if I have missed this homoaromaticity, I'll cover this again, right? So why this molecule is special, guys? You see here, this part, this carbon 2, carbon 3, carbon 4, carbon 4, carbon 6. Here you see the pi electron cloud is there, right? You see here 2 to 4 to 6, right? Here you can see here 2, 3, 4, 5, 6. So here you can see this aromaticity is retained. In this part, aromaticity is retained. But this carbon you see, which is this one, Okay, this carbon goes up, and if you see the hybridization of this one, it is sp3 hybridized. So one can say that okay, this carbon is actually your sp3 hybridized. It should also be non-aromatic, but it is not like that. See, various aromatic properties are there in this compound due to the presence of these 6 pi electrons, right? However, these are different. Okay, so these 2, 3, 4, 5, 6, these all hydrogens are of the same kind, which are there along with the electrons. Please remember. Okay, and you know, if you have learned the NMR spectroscopy in the good detail, and if you have followed my lecture, then you can very easily understand when the pi circulation will take place for this electron. So this is de-shielded area. This area is the de-shielded, because the magnetic field would be like that. So all the protons which are outside the aromatic ring, they are the de-shielded. Please remember, they are the de-shielded. I am writing de-shielded. So what is the meaning of that? This H7 and H8, they are the shielded one. They are the shielded one. If they are the shielded, they will have the low ppm value of the chemical shift. Low ppm value on chemical shift scale. Please remember, while all other hydrogens, right, these hydrogens, right, these have the little higher value, because they are the de-shielded. Downfield signal will go there. Okay, so now you left with this one. This HB is there, HA is there. So you see, in that case again, this inner part is basically what? This is the very shielded part. See, if outside the ring in the NMR spectroscopy is if outer area of the aromatic compound, outer region of this aromatic compounds are de-shielded one, then inner areas are the very shielded. So this hydrogen actually lies in the shielded region, and when it lies in the shielded region, so it will have the very low value of the chemical shift, near to 1 ppm, or say it can go up to negative value, right, because it lies in the shielded area. So this HA, so I can write here, this HA will have the negative chemical shift. Negative chemical shift. Okay, and that means this HA should belong to the option 1. So you can check whether HA is belonging, sorry, it was not HA. HA is here. This was HB. This was HB, guys. Very sorry. This was HB. Okay, and so I have to delete this also. So that means in that case your HB should belong to the negative chemical shift. Very sorry. Okay, so check in the options whether HB is belonging to 1 or not. So in that case, HB is belonging to 1. This could be your answer. But in option 2, HB is belonging to, this cannot be your answer. You can immediately discard the option 2. And if you check the option 3 here, HB is again belonging to 1. That means 1 or 3 either could be the correct one. But in option 4, HB is belonging to 4. That means it is somewhere here, but it is not true. So you can also discard this one. So again you left with the option 1 and the option 3. Right? Quite impressive, this one. But I already told you these two protons, H7 and H2, H7 and H2, they will have the upfield chemical shift. Okay, so and these protons which are actually in the de-shielded region, they will have they are the de-shielded, they have the higher chemical shift. Okay, so here you can see here H2 to H6, basically it is 6 actually, right? I can write 6 here, 2 to 6, basically H2 to 6, this was the option, right? So H2, H6, like all these, they are the de-shielded one, they will have the downfield chemical shift. You know the downfield chemical shift is the 8.5. Okay, that means D, in that case this D should belong to 4. So check in the options whether D is belonging to 4. So in the option 1, D is belonging to 4. But in option 3, D is belonging to, which is not true. So option A is looking the correct answer. You can blindly mark this option 1 as the correct answer. right? Option 1 is the correct answer. But if you want to go further, then I already told you this 1 and 7, this 7 and 2, sorry, this 2 and 7, they will have little higher chemical shift. Okay, not 2, very sorry, this one, very sorry, this one. These are the deshielded. This 1 and 7, they are the shielded one, right? So they have the upfield chemical shift. Okay, upfield chemical shift near about 6.4. So 1 and 7, C can match with the 3. C can match with the 3. And you see here C is matching with the 3 in the option 1. So this is the correct answer. Okay, and what you left with, that can correlate with the 5.1. That means this HA. Okay, because there is very large chemical difference in between these two. This is negative and this is near about in the aromatic region, which is 5.1. So this is how you can explain this problem also. But this problem is quite interesting and a good problem which involves the lots of the concept actually. Right, now moving to the next problem, what it says. Right, my next problem says that the 13-1 proton and MR spectrum of the diamagnetic complex of the MER, that is meridional. Right, meridional means they are the three isomers, the three ligands would not be in the same phase. Okay, and for transition metals actually, for this I is actually 0, quantum number is 0, expected number of resonance, that means how many peaks would you observe for this one. And here you see in the previous lectures also I told you, whenever you have this small bracket sign and inside this small bracket if you have any nuclei, it shows the decoupling. That means it is phosphorus decoupled spectrum. That means this proton will not affect the phosphorus NMR spectrum. Please remember. Okay, but to solve this particular problem, you have to know the structure of this particular compound. So this is the octahedral compound, and it is the meridional, not facial. So all the structure would not be in the same phase. So what I can do, I can draw the structure for this one. This is your, very sorry, I can change the color. So this is your metal in the center, and these are the square in one plane. This is above the plane, this is below the plane. Okay, so if you want to draw the meridional isomer, see I have made an extensive lecture on the isomerism of these class. Again you can go in the search bar, type stereoisomerism in coordination compounds by tetrahedron chemistry classes, then you will find my lectures in the detail. Okay, and so I am drawing this one. So what I can do, I can straightforward write PR3. It could be trimethyl phosphine, or use phosphine, or you try ethyl phosphine, anything it could be. Okay, and again it is PR3. So they are in the opposite corner, and then rest of the last PR3 you can put anywhere, it will not make any difference. So it's up to you whether you put it here, if you put it here, if you put it here, if you put it here. So this can take any orientation. This will not change the overall structure of the compound. Now you left with the three chlorines. What you can do, you can write the chlorine here, you can write the chlorine here, you can write the chlorine here. Okay, and if you mesh them, then what you will find here, you see what I can do. Yes, just like that. This is basically the plane of symmetry. This is the plane of symmetry which renders these two PR3s are same. When these two PR3s are same, guys, it simply means you can mark this phosphorus as 1 and this phosphorus as 1 and then this phosphorus as 2. So total you are having the two kind of the phosphorus. When you have the only two kind of the phosphorus, then you will get the two signals in the spectrum, right? So only you can see here this my option C is the correct one, right? Because two kinds of the phosphorus are there in that case. See, the question is not asking the multiplicity or splitting pattern, all these things. It's simply asking the number of the signals, which you have answered actually. Now moving to the next problem, what it says. Now next problem is another important and interesting problem, which again involves the lots of concept of the general organic chemistry. In the IR spectra, the stretching frequency in centimeter inverse of the carbonyl groups of the following compounds is in the order of. See, you have been given A, B, C and 3 compounds, and you have been given the 4 options, and out of these 4 options you have to correct the correct option. So first of all, the very important thing which I am going to tell you, whenever you have the conjugation, okay, conjugated, I can write here conjugation. So I am writing here conjugation lowers the IR stretching frequency. IR stretching frequency. So and you know what is the meaning of the conjugation? Conjugation means presence of the single double. That means alternatively single double bond would be there. Then you can say it is conjugated. So you can see here this carbonyl, this is double bond, this is single bond, this is double bond. So here conjugation is there. So it will have the lower stretching frequency. For this compound also, this is double, this is single, this is double, this will also have the lower value. That means this option B, which is not conjugated, you see double here and double here, there is no conjugation. Alternate presence of the single and double bond is not there. It is non-conjugated, and it will have the highest value of the stretching frequency. So in the options you can check for the options in which the B has the highest frequency, you can opt for them. Other two options you can discard, as generally happens. So in that case, B is having the highest stretching frequency. Yes, it is correct. Here in that case, it is saying that A, but A is having the conjugation, and conjugation lowers the higher stretching frequency. So this B cannot be your answer. So immediately you can discard this option B. Red I should use option B. And then again in that case, you see in the third option, B is having the highest. Yes, it could be. But C cannot have the highest value because it is like that. The conjugation is there, so you can discard this also. Please remember. Okay. So please, guys, this is very important question, right? Now there is very close competition in these two. So if you see the geometry of this one, this double bond and this double bond, they are on the same side. So basically, this compound C is having the cis configuration. So you can write cis configuration for this one. But for the compound A, you see here double bond is coming here and this double bond going is another direction, right? This is here, this is here. So this is trans geometry. See how trans actually, you can put hydrogen here. So this is the trans geometry, okay? And if it is the trans geometry, you can write trans. And you know the trans isomer is more stable than the cis. Trans isomer is more stable than the cis. Definitely the trans conjugation would be dominant in that case. That means more conjugation in trans form. More conjugation. And the real picture comes from the orbital picture. If you know the orbital diagram of this one, how the orbitals in the hybridization going on, then you will be able to understand the thing. But right now you can understand in that manner, trans isomer are more stable, then you can say that the conjugation is also more prominent for them. So here in that case, and in that case less conjugation would be there. Less conjugation. So when the conjugation is more, IR stretching frequency would be low. So in that case for A should have the lowest stretching frequency. And you see here in option C, A is having the lowest frequency, but option A, it is in the intermediate one, which is the wrong one. So you can discard this option also, but you left with the option C. And again, it is very important question, and it involves the concept of the general organic chemistry. Now moving to the next problem, what it says that, right, somehow actually I missed this problem, the screenshot of this problem, so I have written by my hand actually, handwriting. So what it says that the phosphorus decoupled proton NMR spectrum of cis diethyl phosphine dichloroplatinum compound is comprised with the satellite peaks of the 195 platinum 33.8% abundance in NMR active, is NMR active only. So you can close this one. So what it is saying that you are having this particular compound and this platinum is there, and this platinum is having the two isotopes, okay? But in this two isotopes, the active nuclei is this 195. Please remember, this 195 is active nuclei, and another isotope, another isotope of this platinum, which is 194, and that 194 is actually inactive nuclei, okay? So how you solve the problem, you see here, I can write here in that case, if you take the 100%, right, if you take the 100% and out of this 100%, if you subtract 33.8, okay, percent, then you left with the 66.2. So this 33.8 is what? It is platinum 195, which is NMR active, and will do splitting, or will do splitting of the signal. Please remember. And this 66.2, it is platinum 194, and it is NMR inactive. And when it is NMR inactive, no splitting would occur in that case. Sorry, my bad handwriting. No splitting would occur in that case. And satellite peaks always comes due to the isotope which is less abundant. Okay, which is less abundant. So splitting is there in that case. This platinum NMR, which is actually your 33%, and this will give you the satellite peak. This will give you the satellite peak, which, because it is less abundant. More abundant is NMR inactive. So what you can do, you can draw the structure of this one. Say platinum in the center you can write, and structure is saying it is cis, okay, and it is a square planar type of the complex. You can write PET whole thrice, you can write PET whole thrice, then you can put chlorine here, then you can put chlorine here, and then you see this is the plane of symmetry. This is the plane of symmetry which renders this phosphorus and this phosphorus equivalent, right? And if this is inactive, if you take that, if you take this that example in which this is inactive, say you are taking 194, platinum 194, it is inactive, so you will get only one signal like that. Okay, and you know this inactive part is major part, right? This one. And but if it is the active one, if it is active, what will happen? The singlet which is given by the phosphorus, however phosphorus are equivalent, and if it is 195, phosphorus 190, platinum 195, so this platinum will split that singlet into a doublet, just like that. I can write here this doublet, okay, and that doublet will have the intensity of half of this one, 33.8, half of this 33.8. So if you check the half of this one, it should have the 16.2 roughly, it should have the 16.2 roughly, okay, and that the center part would have 66 point, where I have calculated this one, 2. So the overall structure would look like that. So this is for phosphorus when platinum is inactive, this is then platinum is active, and overall spectrum would look like that. Okay, this is what, 16.2, this is 16.2, and this is 66.2. Okay, so this is how actually looks like. So what actually happening in that case? So how you can now you can check the options actually. Option A is the triplet, option B is the singlet, and D is the doublet, and Q is the quadret. So you will get the singlet in that case. Why? Because the satellite, you see the satellite peaks of this one comprised of just like that, but the actual answer is little different, and it will give you the singlet. So singlet is there along with these two. You cannot say it is giving the triplet, right? Because question is saying that the phosphorus spectrum of the cis is comprised with the satellite peak, right? So with the satellite peaks might mean this satellite peak, and with this singlet. Singlet is there with these two satellites. Okay. Now moving to the next problem, what it says that, right, this problem is again looking a very good problem, very nice problem, and this lecture is also taking too much of time, but it is very important to actually complete this lecture in one go actually. That's why I am more interested in these two. So what the question says that partial spectroscopic data. See guys, when I saw this question for the first time way back in the 2 or 3 years back, right? So I was not impressed with this question because data is actually quite rough data, and with this rough data you will never actually solve the problem. But nonetheless the question is given here, So we have to look for the options also. But again, I already told you the trick in that case. Partial spectroscopic data in the NMR spectrum, you see the proton NMR spectrum. If you check this proton NMR spectrum, what is given here? 2 doublets. 2 doublets means para-di substitution. 2 doublets means para-di substitution. Para-di substitution. So guys, you see sometimes in the lecture you will find some noise. This noise actually is coming from my laptop itself, because there is a problem with the Ryzen series. I have purchased this Ryzen laptop, and that actually is having this heating problem. Okay, so that sign is actually that sound is actually the sound of the fan which is revolving inside the laptop. See, please avoid that. I'm sorry for that. So this is para-di substitution, but para-di substitution is there, so you can easily discard this option C, because it is what you see. This is your ortho, this is beta. You can discard this one, and again you can discard this one also, option A. So you actually discard the option A and option C. So your final answer would be like that, would be in between your B and D. Now you have to select which one is the correct. So again I am giving you the hint actually, how we can how we can very quickly conclude this question, whether which is the correct answer in that case. First of all, you see this B is the ester, and this C is also the ester. Okay, and when you have the esters, then when you have the aliphatic ester, rather I can write the aliphatic esters. Aliphatic esters and non-conjugated. Aliphatic esters, they have the carbonyl frequency basically between 1750 to 1735 in the IR spectrum, centimeter inverse. It is given here in the where is the IR spectrum? Yes, an absorption band at 1724. But for aliphatic esters, actually for aliphatic esters, it is in between this range, but this value is given 1724, which is quite low. But please remember, when your ester is conjugated, I can write here conjugated ester. I already told you, whenever the conjugation is there, conjugation lowers the carbonyl stretching frequency. For conjugated esters, the carbonyl stretching frequency is roughly 1725. Right, and that 1725, which is 1724 here, is given in the question. And you see here, this carbonyl is conjugated with this double bond. This is conjugation. This should have the lower value of 1725, but this ester is not, this ester carbonyl is not conjugated with this ring. It should have the value in between 1750 to 1735. If you have this much of basic knowledge, then you can very easily jump to the conclusion that my option B is the correct answer. So you can very easily write the option B if you have the knowledge about the conjugated. Again, you see the general organic chemistry plays a very, very important role. Okay, so there is no need to go further, and especially I am not interested to go in the detail of this particular problem, because personally I didn't like this problem. Okay, now moving to the next problem, what it says that the structure of the compound displaying the following characteristic spectral data, where IR value is given 1720 centimeter inverse, and proton NMR has this following structures, following spectral properties. First is you will get one proton singlet, which would be broad, and the chemical shift is 6.2, and then you will get another signal at 5.5, which is again broad singlet, and one proton is there, right? And then at 4.2 you will get the quartet, 2 proton quartet, and 2.0 you will get the 3 proton singlet, and 1.1 you will get the triplet, which is corresponding to the 3 protons, right? So how we can solve such problems? It's quite easy guys. You see what is given here. You have given this IR value, okay, which is your 1720, and you know, whenever this 1720 is given, you have seen in the previous slides guys. If I go back, and discuss the characteristic pattern. You see here, in this case again 1724 is basically what? Conjugated ester, as we have seen, right? So when you have been given this IR value near about 1725 or 24 or 20, it is actually the conjugated ester. So you have to look for the ester which is conjugated one. Okay, so you see the option A is the ester, but this ester is not conjugated. You know, conjugation means presence of alternate single and double bond. So here double bond is there and no single bond, and this is single bond, and after that no double bond, right? So it is not conjugated one. So that means that ester cannot have that much of lower IR stretching frequency, right, as we have seen. So you can discard this one, and then you may go for the another option. You see here, this option B is here. This is again, you see, ester, and that ester on the left hand side, it is conjugated one. So this may give you this value of 1720 centimeter inverse, right? So this B could be your answer. I am not rejecting it. Then coming back to the option C, what option C says? See, this is carbonyl group, but it is not conjugated with this one. So again you can discard this option C, right? So you immediately discard this one. Then you go for the option D. What option D says? Option D, you see, it is a ketone. It is simply alpha beta unsaturated ketone, and this ketone actually, right, it is not ester. Please remember, this is the key here. This is the ketone which is the conjugated one, but it is not ester. And you know, the for ketone this IR value is quite high. For ketone this IR value is quite high. So according to me, it is sufficient to reject this option third also. So on the basis of this IR, I am rejecting this one also. So what we left with the B, that means option B is my correct answer in that case. If you want, then you can give the correct, you can give the chemical shift also, right? You see here, this is your CH3 and two hydrogens are here. Of course, this one will give you what? It will give you a triplet, and that triplet should correspond to the 3 proton. Why 3 proton? Because CH3, 3 protons are there, and in the vicinity 2 protons are there. If you apply 2Ni plus 1 rule, it will give you the triplet 3 proton. And what would be the chemical shift for this 3 proton triplet? You see, 3 proton triplet, it's a simply aliphatic proton, so it will have the chemical shift of 1.1. So what you can do, you can write 1.1 ppm for this one, right? And then if you move further for this CH2, this CH2 actually is connected with CH3, so it will give you the 2 proton quadrate. So for this you can write 2 proton quadrate, right? I can write like that for these 2 proton, and it will give you a quadrate, right? 2 proton quadrate. And since this quadrate is actually near to the oxygen, which is electron withdrawing in nature, so obviously this quadrate will not be in the aliphatic range like 1 to 2 ppm. It would be certain somewhat downfield. Here you can see it is 4.2 quadrate at 2 proton, which is due to this oxygen also. The chemical shift is basically for this is 4.2 ppm. Okay, 4.2 ppm. And then if you go further, investigate this structure, and then you are having this CH3 here, and which is this CH3, and here you see nothing is there. So for this again you will get a singlet, but here you see the sp2 carbon is there. This sp2 carbon is basically somewhat electronegative, so this CH3 would be little bit downfield, right, compared to this CH3. So another CH3 you will get here, and the signal for this CH3 where it is, yes, you see 2 it is a 3 proton singlet which is having the chemical shift of 2.0 ppm. Okay, and then you left with the 2 hydrogens attached here. So you can write 2 hydrogens here. One is like that and another is like that. You see, this hydrogen actually is in the environment of this carbonyl group, so this would be downfield. So it will give you the signal, broad signal, right? And that broad signal, basically it is involved in the ketoenol type of that isomerism, right? So when you have that means it will rapidly exchange and converts into the broad structure, broad shaped peak. And since it is converting, it will give you the singlet also, right? So here you can see this will have the 6.2 ppm value, and that 6.2 ppm value you see here, this is 6.2 broad, singlet one proton because it is involved in the kind of the keto-enol isomerism, right? And this then you left with this proton, and this proton will give you the chemical shift of again 5.5 ppm, and that would be again the broad one because equally it is also involved in the keto-enol kind of the isomerism. So if you make these kinds of the this kind of the interpretation, or these kinds of the approaches to actually write the to find the right answer, then you will be able to solve. However, for me actually it is quite sufficient to say that it is a conjugated ester, right? So I will blindly mark this option as the correct option. Okay, now moving to the next problem. Right, so this is my last problem, guys. I think this is my last problem, and what it says that the compound P undergoes a pericyclic. So this is compound P. It is undergoing the pericyclic reaction, okay, under photochemical conditions to give the compound Q. In compound Q, the relative stereochemistry and the chemical shift of the methyl groups respectively. Okay, that means this compound undergo the pericyclic reaction, and whatever the product you will form, then the stereochemistry of these two you have to actually make, you have to decide, okay, and the nature of the compound also you have to decide, as well as the chemical shift also. So first of all, the very important thing, guys, you can remember in that case, this is the electrocyclic reaction under photochemical condition. So if you have followed my lecture on the electrocyclic reaction, then this problem would be easy for you, and if you don't know the trick how to solve this one, right? So first of all, you see here, this compound basically what can happen, I am telling you how. See, first of all you should know this is electrocyclic ring closure, and how many electrons, how many bonds are there? 1, 2, 3. So see, this is my way of explaining actually, right? So only 3 bonds are there which is involved in the reaction. And if someone of you have seen my problem on the pericyclic reaction, then they can easily recall. I actually made a trick for this one on mnemonic. Electrocyclic ring closures, we write ETC. ETC, that means even number of bonds under thermal condition can go the Kahn rotation, right? So the opposite of this one, O, P, C. If you have the odd number of the bonds and you have the photochemical reactions, then again it will give you the Kahn rotation. So if you check here, bond 1, bond 2, bond 3, which are involved in the reaction, 3 bonds, which is the odd number. Condition is given photochemical condition, so these two will undergo the Kahn rotation. Kahn rotation means, in the pericyclic reaction, both the rotation will happen on the same direction, either clockwise or anti-clockwise. Please remember. Okay, so how we can explain this? So this undergo the Kahn rotation. Kahn rotation means, if for example it is going in the clockwise direction, like that. So this will also come in the clockwise direction, right? And simultaneously what will happen in that case, the electrocyclic ring closure will occur, and for this electron pair will come here, and this will go there, and this will come here. Only this part would undergo in the reaction, and this actually undergoing Kahn rotation, so this will go up. That means this methyl will be upside, and since it is also in the clockwise direction, so this will come down. So this is up, this is down. That means trans geometry would be there. Please remember, trans geometry would be there. So you can see first what we can do. First we can draw the structure. How we can draw? Right, this, and then again I can draw ring here, and then I can connect them like that, okay. and say this methyl has gone up, this is Me, and this methyl came down, dashed wedge. So this is methyl, that methyl is actually alpha methyl, and that methyl is the beta methyl. Alpha is below the plane, and beta is above the plane. And then you have seen the electron has moved, this electron pair has moved from here to here, which is there, and this has moved here. So what you can do, see, first of all, you don't need to touch the remaining part. See, you don't need to touch this and this. Sorry, I should use this color. This and this double bond will remain same, this will remain same, and these two will remain same, and this will come here, okay, and this will come here. So this is the final product, okay, this is the final product. So this is the trans geometry, because this is alpha, this is the beta. So you have to look for the options where the trans option is given. So B and C is saying trans, while A and B and D is saying trans, A and C is saying cis. So you can discard A and C. You can discard option A and option C. Okay. Now anything between B and D could be correct. Now we have to apply the concept of the aromaticity. So if you count the total electrons in the whole system, 2 to 4 to 6 to 8 to 10 to 12 to 14. 14 electrons are there. That means 4n plus 2 equals to 14. Okay, so n equals to 3. It is following this condition, that means it is aromatic. This compound is aromatic. Okay, and I told you in the aromatic compound, the region which is inside the ring is very highly shielded region, and these two methyls are lying on the shielded region. When they are in the shielded region, they should have the very high chemical shift. That means very high chemical shift means upfield shift, which is actually the negative value, right? So in these two trans, option D is saying that it is having the -5 of the value. So what you can do, you can mark this option D as the correct answer, right? So this is how you can solve the problem. So this lecture is actually quite lengthy, because I have solved 2 more problems from the inorganic part, right? Phosphorus NMR spectroscopy. That's why it took actually the long time. But I have done this lecture. I hope you understood the concept well, right? And if you are watching video for the first time, please subscribe the tetrahedron chemistry classes. Okay, do share with your friends, and please don't forget to like the video. And if you are a new subscriber here, kindly check the tetrahedron chemistry classes playlist. You will find lots of contents related to the CSIR NET examination as well as the GATE examination in this channel. Okay, so that's it for today. We'll meet you again with the 2019 problems in the next lecture, maybe 1 or 2 days later. Thank you very much.